Hi everyone, and welcome to part 2 of our lesson this week. I hope that part 1 and the gizmo went okay. If you haven't had a chance to look at the gizmo yet, I do highly recommend it. It is really great, especially if you're a picture person like me. It kind of really shows things really clearly in a way that is a little bit difficult to do online. So I do recommend doing that if you haven't already. But if you have done both those things, just grab the note that goes along with today's lesson and we'll get started. Okay, so in the video that I had posted with the gizmo, they talked about this idea of the law of conservation of mass. And so in 1789, there was a scientist called Antoine Lavoisier who recognized that matter cannot be created or destroyed. And so he was the one who developed this law of conservation of mass. And basically that just says that in chemical reactions, no mass is lost or gained. So we can't have something just appear out of thin air, and we also can't just have something disappear into thin air. So there's never going to be mass lost or gained. It can change, and it can change the shape, it can change the way that it is, the actual chemicals that are in it can change, but they're not going to be lost or gained. Nothing is appearing or disappearing. And so to kind of simplify this, the way that I always like to remember it is that you always need to have your reactants equal your products. So the mass has to be equal on both sides. So if we kind of look at some examples of that, and this isn't on your notes, so don't worry about writing it down, but just kind of take a look here. If we're talking about mass, if I start with 3.81 grams of magnesium, 9.92 grams of oxygen, and I'm combining those to make magnesium oxide, well, my mass needs to equal whatever I started with. So you can almost think about it a bit like a math equation. I need to add my two reactants, those masses there, to figure out what the mass of my product needs to be. So if I add those together, I get 13.73 grams. And so that is what the mass of my product, my magnesium oxide, needs to be. And I've got a picture of a balance here because that's exactly what we're doing. We're trying to make sure that our reactants and our products are balanced, that those masses are the same, because we don't have anything that's appearing and we don't have anything that's disappearing. So it has to be equal. If we look at one more example of that, a little bit more complicated, but exact same idea. We've got two reactants here. We've got copper 2 oxide, 6.12 grams of it, and we've got carbon monoxide. We're not sure how many grams we started with of that. And then we're producing copper, 4.76 grams, and carbon dioxide, 6.72 grams. So if we have this mystery here, it's easy to solve because we know that this combination here has to equal this combination here. So again, if we make that into a bit of a math equation, we add up our products. We see that our products equal 11.48 grams. So our reactants have to equal 11.48 grams. So to figure out this little mystery number here, we can just rearrange and find that there's 5.36 grams that we're missing on this side. So that is our mystery amount. So we had to have started with 5.36 grams of carbon monoxide. We're not going to do problems like this going forward. That's why I didn't have you write it down. But just to get the idea of that masses need to equal on both sides of our equation, that we've always got the same mass on our reactant side and our product side. So for us, to make sure that the mass remains equal, we have to make sure that we have the same number of each atom on both sides of our chemical equation. Our reactants need to equal our products. So that's that same idea, but now we're talking about atoms instead of mass. And so if you take a look at these pictures, if we had a chemical equation where we started with H2O2 and we were creating H2O, if you look at here, we've got 2 hydrogens, 2 oxygens, 2 hydrogens, only 1 oxygen. So the balance has been tipped. It's heavier on this side, and our mass would be greater on this side than this side. And so we don't want that. We want it to be equal, because this oxygen molecule here can't just disappear. It has to have gone somewhere. So we need to figure out how to balance that. At the same time, if we add in another water molecule here so that we have 2 oxygens, look at that. All of a sudden we've got way more hydrogens. We've got 4 hydrogens and only 2 on this side, so that we've just tipped the balance the opposite way. So if we add 2 more hydrogens, there we go. We've got a balanced scale here, and that's what we want. We want to make sure that it makes sense that if we started off with 4 hydrogens, they don't appear or disappear. We've got them on the other side. Same with the oxygens. We've got 2 here. We need to end with 2 on the product side. And so we're going to go through a process to figure out what this actually looks like when we're drawing out our chemical equations. So how do we do this? We call it balancing our chemical equations. So we're going to go through the steps and the rules now. Okay, what are our steps to balance a chemical equation? We start by doing exactly what we practiced earlier this week. We're going to change our word equations into a skeleton equation using proper naming rules. Now this might be new here, this skeleton equation. It's exactly what we did earlier this week when we just change the names into their chemical formulas. And it's called a skeleton equation because it's kind of like the bones of the chemical equation, but it's not quite complete yet. So that'll make more sense when we go through an example. Step 2 is to count the number of each atoms on both sides of the equation. So kind of just like in that picture on the last slide where we were counting our hydrogens and oxygens on both sides, we want to be able to count the number of each type of atom that we have. A trick is to treat your polyatomic groups as a single atom. Again, that's going to make more sense when we go through our example. And then the hint here is you are going to want to use something I call an ERP chart. And I'll show you exactly what that is when we go through our example. So we've done step 1, step 2, step 3 is going to be balance both sides by adding in coefficients. And this word came from that worksheet we did on counting. That's why we did that worksheet on counting last week, to get familiar with this idea. But coefficients, just as a reminder, are these big numbers in front of chemical formulas. So the subscripts are the tiny numbers right there, and the coefficients are the big numbers before. And it's important to know that this big number, whenever we add in a coefficient, it applies to everything in the compound. So hopefully you found that when you were doing the sheet last Friday. But just to refresh, that 2 here by the water, it would be applied to the hydrogen. So we'd have 4 hydrogen here, and it would be applied to the oxygen. So we'd have 2 oxygen there. So that's a coefficient. So we do have some rules to follow. We love our rules in chemistry. So the rules for balancing a chemical equation are that you can only change the coefficients. You can never change the subscripts. So we will only be changing these big numbers, never these little numbers. And that is super, super important. I would write like 5 stars beside this, because it can be tricky to remember when you're going through and balancing it. It seems really easy to want to just be able to change these little numbers, but we can't do that because that would change the molecule itself. So we can only change the coefficients. And then the second rule is that you don't need to write a 1 as a coefficient ever. They're invisible, just like if we have subscripts that are 1s, we don't write those either. So an example would be here in front of the oxygen. There's nothing written there. So technically there's an invisible 1, meaning that we have 1 O2 molecule. So let's put all of this into action. I think it's going to make more sense as we go through. So our first example is, we've got a word equation here, so sodium and chlorine gas produces sodium chloride. So our step 1 was to change this word equation into a skeleton equation. So that's exactly what we practiced earlier this week. So we're going to change sodium into Na, chlorine gas, remember whenever we see gas, it's going to be bonded to itself, and then sodium chloride we have to crisscross to get our formula. So it'll end up looking like this. So we've got sodium here, chlorine gas, and sodium chloride. When we crisscross our ones, we don't need to write them in. And I have a little picture above. It's going to help as we go through. I hope. I'm a picture person, like I said earlier, so hopefully you find that helps as well. Okay, so we've got our skeleton equation here. Step 2 is that we need to count the number of each atom on both sides using an ERP chart. This is what an ERP chart looks like. So I suggest you always create this chart when you're trying to balance a chemical equation. It just really helps to keep track of your numbers and to be able to double check your work at the end. So E stands for element. So you write down all of the different elements that you have in your chemical equation. So in this case, we only are talking about sodium and chlorine. And then R stands for reactants, and P stands for products. So we're going to go through and we're going to count how many of each of these atoms we have on our reactant side and our product side. So sodium on our reactant side, we've got 1. On our product side, we've also got 1. Chlorine, we've got 2 on our reactant side and only 1 on our product side. So our chart, when we fill it out, is going to look like this. So right away, this makes it really nice and easy to see what you need to balance, because so far, and you can see this by the picture too, so far we've got 1 sodium on both sides, so that's already balanced, but we have 2 chlorines and only 1 chlorine on the product side, so that's not balanced. We need to figure out how to balance that. So step 3 was to balance by adding in coefficients. So if I have 2 chlorines on this side, I probably want 2 chlorines on this side. So if I add in a coefficient there, you can see that by adding in that coefficient, I've added a whole nother sodium chloride molecule, and this number in the chart is going to change to a 2. However, be careful, because this 2 applies to both things in the compound. So that didn't just change chlorine, it also added in another sodium. So this number has also changed in our chart. So now my chlorines are good, but my sodiums are not. So I've got to look at my equation here and think about where I could add another coefficient to maybe make this balanced. I'm going to try adding a 2 in right here. So that will change this number in the chart to a 2. And now I can see that all of these numbers match. You always want to make sure that your reactants equal your products. So I've got 2 and 2, 2 and 2, boom, that is balanced. I can see that really nice and easily with the picture 2. I've got 2 sodiums and 2 chlorines and 2 sodiums, 2 chlorines. So that is what we want. That is called a balanced chemical equation. And so you just write it with those numbers, those coefficients added. And that's it, that's done. So as soon as you have it so that everything matches, you are good to go. Sometimes you may come across skeleton equations that are actually already balanced. And if that's the case, you just need to write on the side already balanced. But most of the ones that we go through, you'll have to go through this process. You'll have to add in numbers. Let's try another one. Okay, so we've got potassium iodide and lead-2 nitrate produces lead-2 iodide and potassium nitrate. So right away we can see that this one's going to be a little bit trickier. We've got a multivalent metal and we've got a polyatomic. So be careful, pause, remember those rules for naming or for coming up with the chemical equation, and we're going to go ahead and do our skeleton equation. So potassium iodide, they're both ones. Potassium's +1, iodine's -1, so when we crisscross, we just get Ki. Lead 2, meaning that the charge on lead is +2. Nitrate, which the charge on nitrate is -1. When we crisscross that, we have to use our brackets. Lead 2 iodide ends up being Pbi2, and potassium nitrate is KNO3. And again, I have pictures here. Hopefully that helps a little bit. So let's create our ERP chart. We've got 4 elements that we're talking about here: potassium, iodine, lead 2, and nitrate. So remember in these steps, I said treat a polyatomic group as an element. And so this is what I mean. We're going to write it as one unit in our ERP chart. It'll really help to keep track of your numbers. Okay, so then we go through and do the same thing. We just need to see where we're starting off from. So we're going to count the number of potassiums on both sides, iodine, lead, and nitrate. So we're going to count, and we should end up with an ERP chart that looks like this. We're starting with 1 potassium on the reactant side and 1 on the product side, there and there. We've got 1 iodine and then 2 on the product side, right here and here. 1 lead on both sides, and then NO3s, we're treating that as a pact. So here we've got 2 NO3s, and here we've got nothing written outside the brackets, so we only have 1 NO3. So if we go through, we can see that potassium and lead are already balanced, but iodine and nitrate are not. So let's start with iodine. I've got 2 on this side and only 1 on my reactant side. So I'm going to go through and write a 2 in front of potassium iodide so that I can add another one in there. So you can see that added a whole potassium iodide molecule here. And now I can go back to my chart and change it. So I've added a 2, which means there's 2 iodines on my reactant side, but it also changed my potassium. So my potassium has become 2 as well. So now I want to fix that because that's no longer balanced. So I'm going to go to the product side where I see potassium, and I'm going to write a 2 in front of there. So that will change my chart to look like that, but it also changed my amount of nitrates there to a 2 as well. And that actually worked out really well for us because now if we go through, let's see if our reactants equal our products. We've got 2, 2, 2, 2, 1, 1, 2, 2. So that is perfectly balanced. All of our reactants equal our products. We can see that in our picture. We've got 2 green potassium here, 2 green potassium here, 2 purple iodine here, 2 purple iodine here, 2 NO3s, 2 NO3s here, and 1 lead on either side. So that is what we want, which means that we can write our balanced equation. So that one was a little bit trickier. We've got a few more things going on there. But again, if you treat your polyatomic like an element, it's going to make it a lot easier for you. So I have included some practice and the solutions as well. Give those a try. And as always, if you guys have any questions, please feel free to email me and I will do my best to help. Have a wonderful day.